This is Professor Jimenez. Today we're going to start with the instruction set. But before working with the instructions in assembly or assembly code, I need to show you this table, which is located on page 29. The table is for the memory bank. And it is very important to know that to remember that port A is located on bank 0. So bank 0 controls port A, B, and C. Also timers, but for the first code that we will do, this is what we need to know. On bank 1, we will the registers to configure ports TRICE A, TRICE B, and TRICE C are located there in bank 1. Bank 2 is for latches A, B, and C, and also for the DAC, okay? And bank 3, the AND cells, which are required for making using the analog to digital converter. Bank 4 for the weak pull-up resistors in ports A, B, and C. So this is a table that we need to use, and we need to know that it is table 3.3. Okay, and now we have to go to the instruction set, which is on page 508, or you can press Ctrl F and in the find box enter instruction set and you will find it. So in this page 508, let me type it. 508. Right here we have the instruction set. So the instruction set is about this. It's a summary of the instructions that we need to use to work with them. Okay, now it's right here. Let me control the illumination a little bit. Okay, and the instruction set has these descriptions for the operational codes or opcodes fields. So whenever we use the word F, is a registered file address, which can be within this range from 00 to 7F hexadecimal. The word W is for the working register, B is for a bit, K for a constant, X is don't care, D is the destination, N is number 01 for the file select registered, and 2 M's, pre-post increment, decrement mode selection, and the abbreviation descriptions are PC, program counter, TO, timeout, bit, C is the carry bit, DC digital carry, digit carry or decimal carry, Z is the 0 bit, and PD power down bit. So those are the most used abbreviations in the instruction set. Now, with respect to the general format for instructions, these are very similar to the ones we saw in the micro sequencers. So, and right here we can see that the opcode, when you are working with byte-oriented file register operations, the opcode takes these fields from 8 to 13. D is the destination, and the file number, the file you're working with, is in location 0 to 6. Okay, so right here you have 7 bits for the file register address, 7 bits. So you can address up to 128. And D is the destination. If D is 0, the destination of that operation will be W. If D is 1, the destination will be a file register that you are indicating. It can be the same file that you're working with. In bit-oriented file register operations. The opcode now it takes these pins 10 to 13, and right here you define the bit address because you are working with 8 bits, and you want to select one of those bits. You have 3 bits available. That's why you have a 3-bit address, and this is the file number, file 026, okay, which is a 7-bit file register address. A literal control operations. A literal is a key, is a constant from 0 to 7. So we have 8 bits. So that constant can go within the range of 0 to 255. It can be written in decimal, binary, or hexadecimal. And right here is the opcode. Okay, there is a decoder box in the microarchitecture that takes care of decoding the instruction right here. So this constant is an immediate value that you can move, you can load into a register or load it into the working register first. Okay, now there are other instructions like call and go to right here. The call and amplify this, yeah. The call and go to instructions only, those right here goes the opcode, and now you have 10 bits for calling or go to, which is a jump, and you need 10 bits because you can jump up to 1024 different locations. So no, it's 11 bits from 0 to 10. So you have 2 to the 11. So that's 248 different locations. For the move LP instructions, okay, literal opcode for the move for moving into another bank, and this is a very important instruction, move LB. So right here goes the opcode for move LB, and right here you have 5 bits because you have 32 different banks. So this is a way to move with this instruction to move from one bank to another bank, and then you can work with that with those registers. Okay, there's another instruction, the branch instruction only opcode, and the literal. Other instructions like FSR, opcode. Okay, and this is a summary of the instruction set. So on the right side you can see the 14-bit operational code. Let me reduce this a little bit, and so right here you can see that the mnemonic operands are on this side. Let me mark here the highlight. The status affected. This is a description of the instruction, and once you have the description right here, you can refer to every instruction. They are placed here in alphabetical order depending on which types of instruction you're working with. Every instruction, the description is here. This is a mnemonic. This is how you write it in assembler code. This is the description of about what every single instruction is doing. The cycles are here. In this case, these instructions require 1 clock cycle. The 4-bit operational code or opcode, it is right here. So where you see Fs, that's the file number you are selecting. But this notice that these 6 bits relate to the opcode, and notice that right here is the D. Only right there. That's the D, and that's for the destination. So if it is going to be 0, the destination will be W. If it is 1, it'll be the file itself. And the status affected for the arithmetic from the arithmetic logic unit, it is those bits that are affected for every one of those instructions, the carry, decimal carry, 0 bit, you see? And there are some notes there that you can see at the end of every table. So in every instruction, for example, let me show you just one of the basic instruction, the most basic one. Right here is let me clear here. Okay. So let's see the instruction clear file, this one. But I don't want to mark the other ones. Okay, this one. Clear file and clear W. Okay, clear file, you have to put here clear file, and right here you define what file you're clearing, you're resetting. So the clear file makes all the bits in that register, in that file, it makes them equal to 0. If the result is 0, the Z bit will be affected, as it says right here. The Z bit will change. Okay, so we will see that instruction in detail. Right here is just a general introduction to these instructions. Another instruction is clear W, the working register, which is the accumulator, and that's how you clear it. Also, the Z bit will be affected. If it is 0, the result is 0, the Z bit will be equal to 1. Another one, complement F, it's a binary complement, a logical complement. You can decrement a file, you can increment to make loops, increment a file to make a counter, a software counter, not a hardware counter, okay? So there is a difference in that. And another instruction like the inclusive OR, how to move data, how to move one file to another destination, how to move the accumulator, move W to a file, how to rotate left a file to carry, rotate right to carry, subtractions, swap nibbles. You can also swap nibbles, and that's a very important instruction, as we will see later. Exclusive OR, this instruction allows you to determine if two numbers or two constants are equal or are different. You can also do that with the inclusive OR and the IOR. Now, the by-oriented skip operations are these: decrement file, skip if 0, increment file, skip if 0. Bit clear is a bit-oriented file register operation, so you can clear the bit you are specifying right here, or you can make it equal to 1. You can set a bit from any file, and of course these files can be port A, port B, port C, and you can turn on an LED, a relay, or another powerful, another bit that you require for communications. Okay, so bit-oriented skip operations, these are you are testing and you are skipping, so these instructions are very powerful. This one, bit test, skip it clear, bit test, skip it set. So you are testing a bit and you are taking a decision. And there are literal operations, so operations that use constants. So add W, add literal with W, add literal, and this one is and literal with W. So this is a logical operation, and this is an inclusive OR operation. Okay, so you can detect if that literal with respect to W, they are equal or not equal. You can move literal to the branch select registers, to the program counter latch high byte. Move a literal to W. This is one of the most important instructions we will see. Okay, that one. Or move LWK. That's how we know it. Uh, and there are other control operations. The most important one to start this topic will be the go to. So jump to this address. You specify the address right here with a label, and the compiler will substitute this label with a constant K. And of course, you can do a relative branch, relative branch with W. This allows you to read opcode lookup tables